this graph that we've got right here, this is a graph of pressure versus temperature. Pressure in millimeters mercury versus temperature in Kelvin. And this would be for a closed container that was evacuated, okay? So that the only pressure that we're measuring is what had evaporated from the liquid. Okay? So this is the headspace of a closed container. You'll remember last time we defined that as vapor pressure. Right? Let's do our little picture right. This one. There we go. That's what vapor pressure is. Just the vapor provided by a liquid in the headspace of a closed, evacuated container. Okay? So how much pressure that vapor exerts, okay? At equilibrium, at dynamic equilibrium. We had decided last time that because a greater percentage of the molecules will be able to vaporize at a higher temperature, if we raise temperature, we will raise vapor pressure. Okay? And that's sort of separate from the gas laws, pressure being raised, okay? but it's kind of related. It has to do with the equilibrium of that vaporization there. So this very first graph here is actually just part of on the last page here. We had this graph of vapor pressures of different substances. Okay? We saw the vapor pressures increasing with increasing temperature, not linear, okay? But it is a general increasing type relationship. So here is for one particular substance, CH2, Cl2. These are all values that I looked up from a table somewhere. Okay? We see that kind of curved relationship. As we've done a couple of times in lab in this course, what we can do, if we have a relationship that is not linear, we can try all kinds of things to one of those variables, and eventually we'll probably find something that makes it linear. Okay? So you can square it, you can cube it, you can take the reciprocal, you can do 10 to the power of. It turns out, in the case of this kind of this data set and a graph of that general shape, if we take the natural logarithm of the y-axis and keep the x-axis, or actually have to do the reciprocal of the x-axis. Okay? So it's a little more complicated than some, but we have to do that variation to both of the axes. If we didn't do the reciprocal of the x-axis, it would look like inversely proportional relationship. Okay? But we do that reciprocal, and then it becomes linear. So natural log of the pressure, 1 over the temperature. That's the reciprocal. Okay? We now have a linear relationship, so the equation for that line, the equation for that linear trend line, allows us to pretty conveniently solve problems and get some information like that. So where it may seem like this kind of equation is complicated and has just lots of letters and stuff like that, the place that this equation directly came from was the fact that a graph of natural log of pressure versus 1 over temperature is linear. Okay? So if we just replace natural log of P for y, and we place 1 over temperature for x, we can see where that kind of fits in with this equation. M is the slope, x plus the y-intercept right there. So that's like what we said for y, natural log of pressure. That's what we said for x, 1 over t. Okay. The new information here in the Clausius-Clapeyron equation is that the slope represents, so slope is, it's a negative, because those enthalpies of vaporization were positive, so there's just a sign change there. But delta H of vaporization, okay, that was the energy required to vaporize a substance, directly related to the strength of intermolecular forces, just like we talked about, okay, divided by R, 8.314 joules per mole Kelvin. Where have we seen R before? Gas laws, ideal gas law, PV equals nRT. You will notice that R is next to T. If we combine those two fractions together, we get RT. We'll probably be able to count, I don't know, 6 different occasions in this class alone where some energy value will be related with RT. Okay? We've got an enthalpy of vaporization over RT. Okay? That stems from the fact that R is a whole lot more than just the gas constant. Okay? R ends up being, if you look at the units there, joules per mole Kelvin, okay, that ends up being sort of a proportionality constant anytime we're relating energy with an amount of something and its temperature. Okay? So it's far more fundamental, far more important even than just the gas constant. Okay? So we're going to keep that in mind. Several times that R formula, that R constant is going to come up, and it's going to come sort of out of left field a little bit later towards the end of the chapter, and it's kind of neat. So the other thing I want to tell you is that the reason this equation is a natural log and then something that's reciprocal 1 over, it's all because of calculus. We're going to talk just a little bit about calculus. Have any of you in here actually taken Calc 1? Okay, so that's helpful. The prerequisite for this class is just an algebra class. Okay? So basically what Gen Chem 2 is, it's a course in physical chemistry. Okay? Physical chemistry is sort of the physics behind chemistry, why chemical principles happen. Okay? So it's a physical chemistry course without a calculus prerequisite, essentially. All of physical chemistry is totally calculus. Okay? It's all the calculus. So what you're getting in this course is the solutions to all the calculus. So we're solving the calculus for you. That's what this equation is. Okay? And it's actually a little bit of a shame because this equation, before we do the calculus, is actually a whole lot simpler, it turns out. So if any of you are going to take more chemistry classes down the line, if you're interested in engineering or chemistry or things like that, the third year chemistry course is physical chemistry. And the first year of that is thermodynamics, which is going to be a lot of what we're doing here. The second year is quantum mechanics. We touched on that just a little bit in first semester. Okay? But that's basically, in physical chemistry, you redo general chemistry 1 and 2, but this time with calculus. So you're getting the basic introduction to it. There are lots of equations. Okay? We have to give you those equations because we can't have you doing the calculus. So that's why the front page of our notes is filled with equations. These are the equations that you'll be provided with. Okay? But basically every single one of these is solving some sort of calculus. And you can even pick out a couple of them. The very first one on the upper left is the Clausius-Clapeyron equation. But there's another one 2/3 of the way down the middle column that looks almost exactly the same. That's an entirely different circumstance. There's a couple of other places where that happens. So there's something to be aware of. Okay? So what this means for us right now in this class is that we can take this slope right there, and that slope is the negative enthalpy of vaporization divided by R, the gas constant. Okay? So if we take a substance, and it's easy to measure vapor pressure, okay? Maybe somebody will do that as part of a lab project or something this semester. It's easy to measure vapor pressure. You do it at several temperatures. Just do that one manipulation to the graph, you can figure out its enthalpy of vaporization, a number that relates directly back to the strength of its intermolecular forces. Okay? So I gave you some pictures of the guys. I started putting some pictures in because I just got a kick out of how these pictures of old scientists, they always have this very stern look on their face, and some of them are actually kind of funny. So anytime we have a linear relationship, we can simplify that by, instead of saying a whole bunch of points and we draw the trend line, we could have just 2 points. Okay? 2 points is the minimum to define a line, a straight line. So this is the 2-point version of the Clausius-Clapeyron equation. It involves just some algebra in making that line into just 2 points. There's just some arithmetic to that. Okay? But the 1 and the 2's are matched to each other. Okay? So time 1 and time 2. We're just taking 2 points in, we're just sort of taking 2 situations. Okay? These capital T's are temperature, okay? Not time, but... and since we're using temperature inside of an equation, especially on the bottom of a fraction, what is it important that our unit for temperature be? Yeah. You could imagine the trouble that would happen if we used a Celsius temperature and our temperature happened to be 0 Celsius on the bottom of that fraction. That's when bad things start to happen. Okay? So here's some information for you. I've given you delta H of vaporization. Okay. There. I've given you R. And then just so we're all doing this the same, let's make a little list of our values. I'm going to, again, highly recommend making little lists of values, P1, T1, P2. Okay. Let's call P1 115 millimeters of mercury. Okay. Let's call T1, because that's associated with P1, let's call that 34.9 degrees Celsius. And what do you have to add to Celsius to make it Kelvin? Let's add 273.15 to that to be precise. Okay. P2, 760. And by the way, just doing this, the question says, what is its normal boiling point? We defined normal boiling point as the vapor pressure at 760 millimeters of mercury. So that's why we plugged in 760 for that one. Okay. And then T2, okay, boiling point, that's just the temperature right there. Okay. So you're given R, you're given enthalpy of vaporization. Look at what happens to P1 and P2 in this. Do we need to convert that to atmospheres or something? Or because what's going to happen to the unit of P2 and P1 over there? Yeah. The unit doesn't matter. It's just sort of the ratio of those. When we see natural logarithm of a fraction, make sure you divide the fraction first before taking the natural logarithm of it. Okay? So why don't you try to start plugging these things in? If it were me, I would rewrite that equation, but then substituting values, appropriate values in there. Make sure not to reverse your T2 and your T1. Pay very close attention to where those are. That will make a big change. Does anybody need to borrow a calculator? There you go. Write in when you substitute R in, don't just write 8.314. Write 8.314 joules per mole Kelvin. Write those in to make sure that they are actually canceling. That's going to be important. Nothing will mess you up faster in a calculation like this than if your units don't cancel. The other thing I'll remind you of before you get too far, make sure your R unit cancels with the delta H unit that's right above it. So these are just numbers, right? Did anybody get a number just for over on the left here, first of all?
1.888286,305.
Okay. You could either get that by doing natural log and then parentheses of the one thing divided by the other, or you could divide them first and then take the natural log. But either way, that's just all numerical. Okay? So you can get that. Write down plenty of extra digits so you don't have rounding errors. You probably don't need to write your whole calculator's worth, but give yourself a couple of extra digits at least. Okay. What was the big thing I was trying to remind you about in this fraction right here? Yeah. So you can go either way. You could convert one of those into joules, or you could convert one of them into kilojoules, but those have to be the same. Okay? Kilojoules on the top and joules on the bottom does not cancel. Right? And I guarantee that if you don't write these units down, as careful as you're going to be, you're going to miss something like that. Okay? Energy values are almost always given in kilojoules per mole. Okay? That's by far the most common way of writing that. But R is 8.314 joules per mole Kelvin. Okay? So you certainly could just put a conversion here. I would maybe just do something like that. And we're not going to worry about the T stuff just yet, but did somebody get a number for just what's in here? That's how I would treat this. If you have sort of clumps of things that are just numbers, you can simplify those. You can multiply and divide them out. And in fact, you have to make that into a number because you get that multiplied by another complex thing over there. So did anybody get something for just what that is? Yeah, that is not what I got. Yep, that is what I got. Negative, right? I have 0.301 written down. And the joules cancel too. So what's just the unit of that part right here? Kelvin? Close. Yeah. How would I write that if I didn't want to make like a fraction or something? Yep. Okay. Per Kelvin. What was T1? I have to rewrite that. Because, and the reason I write this out again, trying to save you guys from making algebra mistakes, when that's just out there, it's like that's multiplied. What do I have to do to start? What's the first thing that I need to do with this that I've got written here to start getting T2 by itself? Add? We got to divide because there's a number. It's multiplied by, in parentheses, this whole thing. Okay? We can't add because we've got this whole thing multiplied. We could multiply through. That's going to make us a whole lot of extra work. Or we could just divide, right, to get that over here. So let's do that. Because that makes it go away there. And then you'll get some number from there. So I want you to see if you can take it from that point. That should solve a couple of the issues that I was seeing as I was peeking. Once you get an answer, should be a number in Kelvin. Make sure it's actually a reasonable temperature in Kelvin. Compare it with your neighbor, see if you got the same thing. What'd you get? Yep. Looks pretty close. 13. It's 15. You might have rounded it just a little bit different. I wonder if it's just because you took 350 minus 273. I would not round that and then do minus 273 to round it. I think that's probably why. Just off just a little bit. And a number. Okay, so let's add. So let's add to bring that over here, and then you'll have that equals 1 over x. So did everybody add to get rid of the fraction over here? You're going to have this just alone on this side of the fraction, so you got to add then to get rid of that, right? Yeah, so we got a number there. Okay, minus that. Okay, so we got to add. Okay. Okay, that's the right order of magnitude. Get the 1.88 divided by 4871. .386, yep, equals 386, yep. No, that's right, that's what I got. 387, okay, so then we just have to add. So you have to do plus parentheses 1 over. Yeah, and when you're adding, do plus parentheses 1 over 308.05, otherwise I think the order of operations might not be right. All right, so here, I'll update a little more of mine. It's all right. Per mole Kelvin. Ah, no, this one was just Kelvin. That's the problem. because this Kelvin here was on the bottom of two fractions, that's what I was missing, right? It's on the bottom here, but it's also on the bottom of this fraction. That's just a Kelvin, so we're dividing by just regular Kelvin, but that makes this one K minus 1. There. Yeah, that didn't quite look right, but okay. 1 over T2 minus 1 over 308.05 Kelvin. What did somebody get for equal 1 over T2? Just doing the addition here. That would do that. Somebody get something for this addition here? 0 point something? Yep, that's what I got. 002855, something like that. Or 2.8585 times 10 to the minus 3, I think. Kelvin. Equals 1 over T2. Okay. How do you solve for a variable that's on the bottom of a fraction like that? If a number equals 1 over x, then what do you have to do to solve for x? You have to take the reciprocal again of that one, right? So you have to do 1 over. So somebody get that number? It's just temperature in Kelvin. Yeah. Rounding might be a little different. I got 349.8. It's close. And then to get that back into Celsius, I got 76.7. If we keep it down to 3 sig figs, is that the same rounding that somebody else and anybody else got? Close? Okay. The two major difficulties of a big math problem like this are units that aren't properly canceling. If I hadn't reminded you of that, how many of you would have just done 40.5 divided by 8.314? Right there. Okay, so good to be honest about that. That is going to require a unit conversion more often than not. Let's just put it that way. Okay. The other common thing that I would see in something like this would be adding first. Okay. You can't add from something unless that whole side of the fraction is this minus that or whatever. Okay? When you've got something multiplied in front of it, you could multiply through, or you could just divide by that to get it out of the way if you've just got numbers over there. Okay? Then our whole side of the fraction is that which we could add from. Okay? And believe it or not, I've seen lots of mistakes just right in this step, right here. Okay? Solving for a variable that's on the bottom of a fraction requires taking the reciprocal. Okay? It requires doing 1 divided by. So I would consider 3 major portions where I would identify common errors. So you're going to have a question like this in your Mastering Chemistry, I'm sure, but it would be really great if you could go through some of the practice problems at the end of the chapter, just on a couple sheets of notebook paper, just to make sure that you can do this math on your own, and see if you can do it without looking at what we did here. Okay? That's going to be the trick to it. And I know for some of you, even those of you that have taken calculus, the algebra is probably a little bit rusty. That happens, but now's the time to be thinking about it. Okay. All right. What must the pressure be to boil water at 25.0 C? Vapor pressure of water is 40.1 millimeters of mercury at 34.1 C. So that's just one pair. We could have given you any vapor pressure of water. We could have given you the boiling point of water. We could have said that it is 760 at 100. That's the regular boiling point. That would have worked just the same. Okay. So let's make a little list here. I'm not going to just set you off on this one because I want to talk to you just about one thing first before you do that. But you'll do plus 273.15. So I just called that T1 because that was the first temperature, but what must be the pressure? So P1 is what we're solving for. P2, 40.1. Now make sure you put parentheses. I would even do it in the formula over there, because I've seen a lot of people not understanding that those are parentheses inside of that natural logarithm there. So it's going to be 40.1 divided by P1. Okay. And then all the rest of this over on the right is numbers. Okay. So what I want you to do right now, I want you to copy this down because we'll deal with that in a second. But I want you to substitute all these numbers in, okay, and just simplify that and just get a number over here. Okay? So all those things are going to be numbers. So why don't you just take a couple of minutes and crank through those numbers to make sure you get your parentheses in the right place, and that's just cranking it through. Then we'll worry about the left. But don't forget the first thing I warned you about on the last page. If I get the right answer. P2. Seven. There we go. Anybody get a number yet? That's what I got. If you did not get that, make sure you multiplied by 1,000 to convert your kilojoules into joules. Or I guess you could divide 8.314 by 1,000 to get kilojoules per mole Kelvin, but that's... Say that again? Oh, for units. Well, what do we think here? You'd have joules per mole. You'd have joules per mole Kelvin. You'd have per Kelvin over there. Let me write this out. You can also sort of look at what happens over here to get a clue about the units, but you can actually just write the units if you want. Kilojoules per mole. And then I had that times, right, just to convert that unit, that is joules per mole Kelvin. So all of those cancel. But this is, it's the same mistake I made on the last page. This is the Kelvin beneath two fractions, right? It's on the bottom of the big fraction, and it's also on the bottom of this fraction right here. Right? That's like that. That's so I think they cancel, personally. You have per Kelvin over there, on right here, per Kelvin, and you've got just per Kelvin. So that's just regular Kelvin, and that's per Kelvin. Okay. Also, maybe if you didn't quite get that answer, typing this in, I would have done that times 1,000 divided by R times, and I would probably use that parentheses in my calculator. And if I had them already in Kelvin, I could do 1 divided by minus 1 divided by and close that parentheses. Okay? You do need parentheses because this whole thing is multiplied by the subtracted sum there. Okay? If you didn't quite get that answer, maybe compare with somebody else that did. But then we have the issue of this. This is the complication in this one here. So you may be tempted to divide both sides by 40.1, but that doesn't work. That 40.1 is inside of a natural logarithm. We have to somehow get rid of that natural logarithm. What is the opposite mathematical function to a natural logarithm? Anybody know? E, lowercase e. And if you ever forget about that, your calculator sometimes gives you a hint, because most calculators have e to the x printed above the natural log key. So a lot of times the opposite functions are just 1 over each other. So we have to take e to both sides. You have to do e to the e to the and when we do that, those two are opposite functions. So we'll just have a fraction over here, we'll have a number over there, Did anybody get the number over here for e to the 0.486? Okay, 62627 I think is what I got. If we do e to the, you can use answer. If your calculator has ANS, just do e to the answer on that. If you got a two-liner graphing calculator, so you're not having any kind of rounding errors, 1.626278. Okay? And I've seen students make a mistake at this step right here, actually far more often than the last step of the last page. Okay? Most of us, I think, can do the reciprocal of something, but solving for this one, I've seen lots of people make mistakes. What do you have to do to solve for P1? Right there. You could, yep. It's a matter of cross-multiplying, right? We can multiply both sides by P1. Okay? That gets the P1 up on top over to the right. And then we have to divide both sides by the 1.6 to get it down on the bottom. Okay? So we have to do and you'll see how nicely the units work out, because there's no unit over here. That gives us a pressure with the same unit as the pressure that we started with, which is what? Yep. I'm going to do 40.1 divided by answer, because that 1.6 was in my calculator before. So, yep. That's what I got. Millimeters of mercury. So it required no unit conversion for the pressure, because, again, those pressures inside of that logarithm are just a ratio. So at our very last step, we add that pressure unit back in. Okay? So this step right here is one that you could get messed up on a little bit. It really helps to draw a parentheses around that fraction for the natural logarithm, so you're not tempted to dismantle that fraction before you get rid of the ln. Okay? And then cross multiply properly. Alrighty. I'm sure you will have to do a problem like this. You will absolutely have to do a couple of problems like this in mastering chemistry, solving for either of the variables. Your quiz, I do not think, will go up to this point, so you'll have a little bit more time, but you will for sure have to do this on the exam. Okay? So practice this. I know it's crummy to get points taken off in a chemistry course because of algebra, but, you know, be thankful we don't make you use the calculus. Let's just put it that way. Did anybody have any questions about those? That's an equation you'll be given, but